big suckers?
No.
Yeah.
Alright, I hope it doesn't bother anybody that we turned off the lights. It's kind of hard to tell what's going on with the lights on. Today we're going to be talking about linear equations, specifically linear equations which are in standard form. As I understand, you guys are still on Chapter 2. This, however, is a Chapter 3 lesson. It shouldn't pose too much problems, though. I think you all should still be able to pick up on everything that we'll discuss. First, however, let's take a look at some linear equations. So the graph I have here.
I need Chelsea for just a minute, please.
No. She said she.
Okay, give them your attention now, everybody. I think you need to move forward.
Alright, so the graph I have here is indeed the graph of a linear equation. Specifically, it is the graph of this linear equation, x minus y equals 0. One thing to note, can anyone tell me what all of these graphs have in common?
Lines.
Lines. A little bit more specifically, what about the lines?
They're all
They are for
the
variables.
horizontal and vertical line.
They're straight.
Well, this line isn't horizontal or
They're
vertical.
crossing.
They do all cross.
They're straight.
Wait,
They
you
are
said
all straight
graphs.
lines.
Did you mean? Did you say line?
I said the graphs of this equation, or of these equations. But I believe you hit on it exactly what I was looking for. These are all straight lines. We call the equations whose graphs are straight lines linear equations. In fact, you can even see the word line in linear. So you know that if you're dealing with a linear equation, you can expect that your graph will appear linear. In fact, as far out as we could possibly go with these equations, we zoom out as far as we can. These lines will always be straight lines. That's true for every linear equation. So let's take a look at some nonlinear equations. That way we can officially determine what exactly it means to be linear. Is this a straight line?
No.
No, it is clearly not. However, these two equations are actually quite similar to each other. X minus y equals 0, x squared minus y equals 0. The only difference between these two equations is that our x term is being raised by an exponent. And thus you can see that the line certainly stops being linear. What do you guys think will go on with this graph where the y value is being squared? Anyone?
Negative to that, would it not?
So what you're saying is it would be a downward facing graph?
I assume, yeah.
Okay. It is in fact actually a sideways facing graph. We could manipulate this graph so that it would be a downward facing graph just by introducing a negative in front of our x squared. But the graph of a function where the y value is the one being squared is in fact a sideways parabola. Either way though, neither of these lines, neither of these equations represent a linear graph. Both of the graphs of these equations are curved lines. So I think it's safe to assume that we can establish one restriction of an equation, and that restriction is that your variables cannot be raised to exponents. So I believe you guys have notes, right? There we go. So can anyone answer this first problem for me? A linear equation, an equation whose graph is a, any suggestions? What was that?
Line.
Straight line.
A straight line. Because in fact, these blue graphs are lines. They're just non-linear lines. They're not straight. So specifically, a linear equation is an equation whose graph is a straight line. You may, in fact, take note that with these other equations, the ones that I also said were linear, perhaps we should hide these blue ones real quick. These other linear equations, they're still straight lines. However, some of these equations have one variable. This equation is just x equals 3. This equation is just y equals 9/2. These two equations here have two variables. So one thing that I think we can safely say about linear equations is that they can either have one or two variables, which will fill in this blank right here quite nicely. Similarly,
Do they have the papers fill these notes in?
yes, they do. I handed them out.
Okay, could I have one too, please?
Oh, certainly. Did anyone not get the notes? Yeah, everyone has a paper? Perfect. So fill these out as we go along. You'll be able to use these in the future to study with and to complete your homework assignments. So we've covered one of the restrictions by examining those two blue graphs. And so what was that restriction? Can anyone say it?
Exponent.
Exponents. Your variables cannot be raised to exponents. So we have our first restriction down. Very good, very good. Let's go back to our graph and analyze some of these other restrictions. The next, as the name may suggest, are radicals, which are just square roots. The graph of a function with a square root in it is very clearly nonlinear. It's definitely curved. Same thing with our y value under the square root. It still is nonlinear. In fact, they very closely resemble some of these quadratic equations which we have. In fact, they almost perfectly line up with it. If we were to introduce a negative in front of this x, you'll see it covers the other half, which the original equation did not cover. Whether you have the positive representation or the negative representation, both of these are still nonlinear lines. Neither of them are straight. Similarly, with our y value in the radical, you can see that it is also a nonlinear line. If we were to change this negative sign to a plus sign, we would get the other side of our quadratic equation. Either way, still nonlinear. So then what would that lead you to assume about this second restriction, which we will talk about?
Radical.
Yes, no radicals. Very good. Two restrictions left. Moving on now to logarithmic equations. You don't necessarily need to know the term logarithmic, however, it's really fun to write, even more fun to type. I decided to do it. But you can see here by the graph of 1 over x plus y equals 0, this is certainly not a straight line. In fact, it actually looks like it's two lines, neither of which are straight. Both have a very intense curve, perhaps even more intense than the previous two examples which we looked at. Similarly, the graph of an equation where two unknown variables are multiplying each other is also rather nonlinear. So, with that being said, we can fill out our next two restrictions.
No logarithmic.
The first of which being,
No logarithmic.
sure, but there's not a whole lot that you can attach that to right now in your current
Okay.
set of knowledge. That doesn't mean a lot to you, right? The word logarithmic doesn't mean a lot to you. But what we can say that you guys can attach to, which you have covered before, is that there are no variables in the denominator, which with this example here, x is in the denominator, and we can see that the graph of that equation is nonlinear. So by saying no variables in the denominator, you cover that restriction. And can anyone suppose what the fourth restriction might be?
No variables in the numerator.
The variables in the numerator. You're close. I would go as far as to say that all of these linear equations have variables in the numerator. This could be expressed as x over 1, this be expressed as y over 1, x over 1, y over 1. Again, all of these variables are in the numerator. So where I see your instinct to say that, because our previous restriction was no variables in the denominator, in fact, linear equations can have variables in the numerator. But if we take a look at this second logarithmic equation, perhaps.
You have to erase it first.
Excellent suggestion. Brilliant. So here's our other logarithmic equation, which resulted in a graph which was nonlinear. What was it about this equation which caused that to happen? What is different about this equation compared to our linear equation here?
The variables aren't being multiplied together.
Correct. So we can say that our final restriction would be that no variables are multiplying other variables. Okay, does everyone have this written down? Yep. Fantastic. So now I'll just give you some examples of some linear equations and some examples of nonlinear equations. We've already looked at several examples of both, but this way you guys can have them in your notes to compare to future equations which you may encounter. So the first example of a linear equation could be anything. You could let your x and y value be scaled by any type of constants. What's important, though, is that we don't break any of our restrictions which we've just gone over. Neither of these variables are raised to any exponent. Similarly, neither of these variables are under any radicals. Neither of these variables are in the denominator of their expression, and neither of these variables are multiplied variables. Therefore, we can say that this equation is indeed linear. This equation also is linear. As I said at the beginning of class, at the top of your notes it states that a linear equation can have one or two variables. This equation is an example of one which only has one variable, your x variable. However, if you check this against your four restrictions, which a linear equation must follow, this x is still not being raised to an exponent, it's still not under a radical, it's still not in the denominator, and it's still not being multiplied by another unknown variable. So we can say that this equation as well is linear. Finally, we don't even have to use x and y as our variables. We could use s plus t, or we could use q plus r. It doesn't quite matter what we use our variables as long as we have no more than two variables, and these variables still meet our previous restrictions, which were no exponents, no radicals, no variables multiplying another variable, and no variables in the denominator. So both of these would also be linear equations. So with that being said, can anybody give me an example of a nonlinear equation?
Yeah. X to the second power equals 0.
Perfect. This breaks our first restriction. We can't have exponents in our we can't have our variables raised to exponents. This certainly breaks that. The only variable in the equation is raised to an exponent, so this is certainly nonlinear. How about another one which breaks a different restriction?
X minus the square root of y equals 0.
Okay. Perfect. How about another restriction?
X times y equals 0.
Okay. That'll be restriction 4. That's perfectly acceptable. How about restriction 3, one that violates restriction 3?
5 over x equals 0.
Perfect. And it doesn't matter what number is in our numerator. If we have any variable in the denominator, it is still going to be nonlinear. This could be 1,000 over x. It could be 0.2 over x, and it would still be nonlinear because that x value appears in the denominator. Excellent. Does everyone have this written down? Super. So now you guys can work on your own and try to determine whether these equations are linear or nonlinear. A simple yes if it's linear or no if it's nonlinear will suffice. But if it is nonlinear, I want you to circle what makes it nonlinear. So go ahead and do that. It shouldn't take long. I'll give you all about 2 minutes to complete this, and then we'll go over it as a class. If you have any questions, feel free to ask those around you as well. All right, it looks like most people are done for the most part. Does someone want to take a whack at number 1? Is it linear or nonlinear? Yeah, what do you got?
No,
It's nonlinear. Why do you think that?
because y is multiplying, x is multiplying to y.
You're talking about this term here?
Yeah.
Exactly. This is in fact nonlinear. How about number 2?
It's non-linear. Oh. Linear.
Okay, well, so I have one person saying nonlinear, others saying linear. Which is it? All right, so we're all over the place. Why do you think it's nonlinear?
Because it's got, I mean, I kind of think it's linear now because there's not a variable in the denominator.
Yeah, I kind of tried to trick you guys, right? It kind of looks like this might in fact be in the denominator. I think in your notes, this fraction is oriented more vertically, and so it's a little bit more clear that it's not in the denominator. But these parentheses here should give it away, that this x is in fact over and understood 1, which implies the x is in the numerator, not the denominator. And thus, this equation is in fact linear. Because our x value is not squared, our y value is not squared, neither of those two values are under a square root. The trickiest thing was, yes, the third restriction, and I could see where that would definitely snag you up. So how about number 3 then? Number 3 doesn't have that type of discrepancy. Is this linear or nonlinear? What do you think?
I think it's linear.
Okay. So this one certainly is linear for the same reasons as the last one was. These variables aren't being raised to as any powers. They're not being taken the square root of. None of these variables are multiplying another variable, and they all appear in the numerators. So then number 4,
It's non-linear.
nonlinear. Very good, very good. Because that x appears under the radical. So this is certainly nonlinear. So next, let's go back to our program here. I have here the graph of a linear equation. I think we can all agree on that at this point. It certainly is a straight line. It doesn't appear to resemble any of those other equations which we determined to be nonlinear. In fact, the equation of this line is given here. 1x minus 1y equals 0. Can anyone tell me what this line will look like?
Would it be like vertical?
I see your inclination for that, but our vertical lines, as we can go up here and reanalyze, our vertical line, our vertical line just had one variable, and that variable was x. This equation, which we're looking at down here, has x and y.
Will be the same.
Why do you think it'd be the same?
Because
Do you have a suggestion?
I have a question about the line that's going through it. Is that like matter, or is it like just nothing, just saying that that's a vertical line there?
You're talking about this line?
No, the one that's like this.
This
That's
line.
line.
That's the graph that we're looking at. That's
Oh.
this equation. Did that answer your question?
Yeah, I thought it was like just a line there.
Oh, I gotcha. No, that is in fact the equation which we're looking at. And now I'm asking, what would this equation's graph look like? So we have one supposition that they would be the same. Can anyone validate that or refute it? What do you think?
Wouldn't it be crossing where 1 is instead of 0?
And why do you say that?
Because it's like 1y, 1x.
1y, 1x. This one also is 1y, 1x though.
But it doesn't equal 0 on the second one.
I see what you're saying, because this one equals y instead of equals 0. In fact, this is the exact same line. Tricked ya. How about this equation then, huh? What would the graph of this equation look like? Same thing. It is indeed, in fact, the same thing. Although this equation varies drastically from the rest of the equations. So then how then can we explain how these equations have the same graph?
Does it all divide down?
You're saying that you can manipulate these algebraically? Is that what you're trying to say? I would certainly agree with that. If we were to manipulate this algebraically, you distribute your 1 into the parentheses, which would leave you with x minus 100. Add 100 to both sides, and your 100 values would cancel out, leaving you with just x equals 1x plus 0, the exact same form of this equation. Similarly, we could derive the first equation. We could derive the first equation from the second equation by subtracting our y value over, and then we'd be left with 0 equals 1x minus y, which is the same thing as saying 1x minus y equals 0. All of this was simply to establish that there are various different ways which we can express the same linear equation. These are, in fact, all equivalent equations. You can tell that by their lines. Their lines follow the exact same points everywhere, throughout all of infinity on the number line, in both the x direction and the y direction. These lines will perfectly match up because these are equivalent equations. The form that we are specifically going to be focusing on today for the rest of this lecture will be this first form, which we call standard form. So the standard form of a linear equation can be expressed as such, where you have a, b, and c as constants multiplying the unknown variables x and y. So earlier I gave an example of a linear equation which did not have x and y in it. We used s and t, or q or r, whatever other variables you'd like to use. For an equation to be in standard form, it has to use x and y. So if it doesn't have x and y, if it has s or t, you would simply just replace them with x and y. This is nothing more than a notational convention. This is just the way that standard form is written. So this is how it has to be written. One thing, however, that is very important, I have it here in this note, which I did not mean to highlight. The first term that appears is your x term, and followed by your y term, and then followed by your equal sign, then one lone constant on the other side of the equal sign. Doesn't matter what these constants are, they can be any number, but as long as it takes this general structure. In addition to that restriction, we have 4 other restrictions. The first of which is that there can be no fractions. A, B, and C have to all be whole numbers. If any of these constant variables are fractions, you would have to multiply your entire equation as to get rid of the fraction. The second restriction we have for standard form is that both A and B cannot equal 0. And this may be the most notationally heavy restriction. All this means is that if A equals 0, B can't equal 0, and vice versa. If B equals 0, A can't equal 0. In fact, we've already looked at some examples where either A or B equals 0. One of them was if we let B equal 0, we would have AX plus 0Y equals C. This term would drop off because it's being multiplied by 0, and we're left with AX equals C, our one variable equation, which would result in our straight line, our vertical line straight up and down. If we let A equal 0, we would have 0x plus by equals c. This term would drop off, leaving us just with by equals c. Again, this is another one variable linear equation, which the graph of this equation would be a horizontal line, which would be much straighter than the line which I drew on the board. It would be perfectly straight. However, if both A and B were equal to 0, we wouldn't have any variables left in the equation at all. Both of our variables would drop off, just as this variable and this variable dropped off here. And we'd be left with 0 plus 0 equals c, or just c equals 0. And this no longer is a line. This is simply just a point on the coordinate plane. So all of that just to say that if a is equal to 0, b can't be equal to 0, and the other way around. The next restriction for a linear equation in standard form is that you cannot lead with a negative. A cannot be equal to, or a cannot be equal to a negative number. If a is equal to a negative number, you'll have to multiply both sides of the equation by -1. It's perfectly fine for b or c to be equal to a negative. We just can't lead with a negative. Again, this is simply a convention of linear equations. Moving on now to restriction 4, which is quite possibly the hardest restriction to identify. So definitely make sure you take very good notes about this one. Must simplify. So let's suppose that our a value is 2, our b value is 6, and our c is 10. Right, so our equation in standard form would look something like 2x plus 6y equals 10. However, this equation can be simplified in such a way that by dividing both sides of the equal sign by 2, these two terms will cancel out, leaving just x plus 3y equals 5. This equation is now in simplest form because your a, b, and c values, which are 1, 3, and 5, are all prime numbers. They cannot be reduced any further. Yet we still satisfy our other 3 restrictions. There's no fractions. A and b, neither of them are 0, which is perfectly fine. And a is not negative. So then this equation would now be in standard form. Or as the initial representation of the equation, though equivalent to this equation, is not in fact in standard form. Does everybody have these restrictions copied down? Good. So now, home stretch, right? So I need you guys to practice these examples on your own. You will need to rewrite each equation so that they're in standard form. After you do that, I need you to find a, b, and c. One thing I'll tell you is that these all are linear equations, so they definitely will all be able to be written in standard form, if they are not already so. This is going to be a little bit harder of an example than the previous example, so I'll give you all 5 minutes to complete this one. If you guys have any questions, feel free to ask. But I expect to see everybody working. Don't just wait until we go over this as a class. I want you guys to come up with your own answers and compare them to the ones that we developed as a class.
Teachers, pardon the interruption, but if you have any students that are dressed up for Red Ribbon Week, would you please have them go to the ITV room at this time so they can take pictures for the yearbook? Thank you.
No one in here is dressed up, huh?
Didn't know
about it.
Folks.
I didn't know.
We didn't know about it.
Yeah, they didn't tell any of us.
All right, you guys are off the hook then.
I have a cat.
Even more reason to enjoy your time while you're here. Okay, so where's everyone at? What numbers has everyone gotten to? Gotten through 2? How about everyone else? Alright, keep working. I'll give you guys 2 more minutes to get as far as you can before we go over it.
Can I have the list, please?
Oh, yeah, sorry.
That's good.
We're on the back side of the page at the very bottom.
Thank you.
You're welcome.
Do all of these simplify?
Some of them are already as simplified as they can be. They will all be able to be expressed in standard form. The only question is how. Okay. Good question. Just for the sake of time, I'm going to go ahead and start going over them. So try to finish up whichever one you're on, and then compare your answers to the ones that we developed as a class. Can anyone tell me how they got the first equation in standard form? How about you? No? You didn't bother to do it?
No.
That's unfortunate. Did anyone do it?
I can figure that out.
I'm still kind of confused about it, like, because you said there can't be any fractions, so do you have to change the fraction?
There's no variables in the denominator.
Well, that's true for linear equations, but specifically for a linear equation in standard form, she's exactly right. There can't be any fractions. So you do have to manipulate this equation in such a way to eliminate the fractions. Before we do that, however, I think an easier suggestion as to how to start this problem to get it into standard form would be to get both of our variables on the same side of the equation. We know that an equation in standard form has to be written in such a way that you have a times x plus b times y equals c, but our y term is not on the same side of the equal sign as our x. What you got?
I subtracted y from 3 over 4, and then I also subtracted it from x because that's what we,
Yeah, what you do to one side of the equal sign, you must do
Yeah.
to the other side. These two y terms will drop off, leaving you with x minus y equals 3/4. So we're definitely closer to being in standard form. We have both of our variables on the same side of the equal sign. However, we still have one of our restrictions being violated, which is no fractions. How do we get rid of this fraction?
you switch it to 3 divided by 4.
I'm sorry, what?
Switch it to 3 divided by 4.
This is 3 divided by 4.
Can you like,
Multiply it by what? By 4? So if we multiply both sides of the equation by 4, let's go ahead and write it as 4 over 1, just so we can kind of see what's going on a little bit easier. These two 4 values will cancel, leaving us just with 3 on the right side of the equal sign. We multiply the left side of the equal sign by 4, we have to be very careful. It's not just going to be 4x minus y. We have to distribute that 4 to both terms on that side of the equal sign. Doing so will give us 4x minus 4y. Is this in standard form?
yeah, because the,
Yeah, you divided by
yeah.
Okay. Let's check it with all of our restrictions so that we can be sure. What was our first restriction? No fractions. Boom, we've taken care of that with our previous step. What was our second restriction?
Both and neither. If A equals 0, then B can't.
Right. And our a here is 4, and our a here, or our b here is -4, neither of which are 0, so that restriction holds. How about our third restriction? Can't lead with a negative. Our a is certainly positive, so that leads us to our final restriction. Can we simplify this any further?
No.
Correct. We cannot simplify this any further, because 4 and 3 share no common factors other than 1. We cannot simplify this any further. Therefore, this equation is in standard form. So we've kind of touched on this a little bit, but what are the a, b, and c values for this standard form equation? Anyone?
A equals 4, B equals -4, and C equals 3.
4, -4, and 3. The one place I could see where people might get tripped up would be b equals -4. You cannot forget that this minus sign turns your b into a negative value. Other than that, I think it's pretty straightforward from there, and you've got it exactly correct. A equals 4, b equals -4, c equals 3. So moving on now to number 2. Who has a suggestion about how to start number 2?
You could, get your x's together.
That is the perfect first suggestion. So we'll subtract both sides of the equal sign by -2. Doing so, these terms will cancel, leaving us with 5 plus y equals 3x. Now what do we need to do?
Get the x with the y, or the y with the x.
Okay, so by subtracting both sides of the equal sign by y, we are left with 3x minus y equals, these two y terms cancel out, equals 5. Is this in standard form?
Yeah.
Yes.
Yes, yes. 2 yeses out of a room full of silences. Can I get anyone else's confirmations? Yes? Okay. This is indeed in standard form. What then are the a, b, and c values?
A equals 3.
What did you get for b
-4.
and c?
5.
-4. Is that just because I have bad handwriting or what?
Would it be
It's a
1?
Y and then-
Oh,
Alright, so our a certainly is 3 and our c certainly is 5. Our b value is what?
-1.
-1. Very good.
Because y is right next to y.
Okay. Number 3 is hidden right here in the middle. What can you guys tell me about number 3?
It's already done.
It's already in standard form.
Yes. Wait,
So then what are the a, b, and c values? So we know that a is our term that is multiplying x. What term is multiplying x here?
1.
1. We know that our c is the term, the constant term on the right side of the equal sign, which is simply 10. What then is our b value?
10.
N. Why n?
I mean 10.
Oh, 10. You think b is 10.
Yes.
Well, our c is 10. Does that change your thought?
No, because 1 times 10 is 10. And that would equal 10 on this side.
I see. So what you're doing is you're dividing our a, or dividing our c by our a value. Is that what you're saying? To get our b. What I would say to that then is keep in mind that b is the constant term which is multiplying our y value.
0.
So is it 1?
I heard a couple of suggestions. I want one of you who just suggested something to say it again.
0.
0.
Oh, not 0. Shoot, that's a c.
1.
So 1.
1, 0. Which is it, folks?
0 because if it would one of your
If you're multiplied by 0, it equals 0, so it can't be 0.
Yeah, very good.
Yeah, because
So if b is 0, then this equation now becomes ax plus 0 equals c, or simply just ax equals c, which is what we have here, ax equals c. So this equation is in fact already in standard form, and we have just identified our a, b, and c values. So I'd say we've pretty much put a pin in number 3. How about number 4? Is number 4 in standard form?
no.
we just have to simplify.
Your x and y has to be on the other side.
Well, the x and y are both on the correct side of the equal sign. And it's in the correct structure. X comes first plus y equals a constant.
Then yes.
It would be. However, your classmates have pointed out a very critical restriction. This is not in the simplest form. All of these constants share a common factor greater than 1. These constants are not all prime, which means that we can simplify them. So to simplify this equation, 2x plus 4y equals 10, what would we do?
Divided by 2.
Divided by 2, which this first constant multiplier would drop off, leaving us just with x, plus 2y equals 5. Now is this equation in standard form?
Yes.
You know that because you checked it with all of your restrictions. There's no fractions. You're not leading with a negative number. It is now in simplest form because we just put it that way, and A and B do not both equal 0. What do A and B equal?
1 and 2.
1 and 2, leaving C as 5. Very good. Finally, number 5, quite possibly the most difficult of the examples. Can anyone tell me how we should start this problem?
By putting your x with your y.
Yeah, if you're for it, to the opposite side.
So moving the 4x to the opposite side of the equation gives us negative 4x plus 1/2 y equals 5. Is this in standard form?
No.
What do we need to do?
Change your fraction.
Okay, so how do we get rid of this 1/2 fraction?
Could you change it to 0.5?
You could, however, a decimal is just another way to represent a fraction. And so while I did only explicitly say standard form can't have fractions, it's implied that it can't have decimals as well. Because a decimal is just another way to represent a fraction. What do you think?
Can you multiply it by its reciprocal?
Multiply it by its reciprocal, fantastic. Which is 2 over 1. Whenever we multiply our first term by 2 over 1, it leaves us with negative 8. Ooh, that's not an 8. Negative 8x plus these terms cancel out, leaving 1y equals 10. Is this equation in standard form?
Yeah.
Check your restrictions. I think you'll
No.
see that we have violated one of our
Simplest
restrictions.
Right, it's not simplified.
I would say, however, that it is simplified because
Oh, it starts with a negative.
correct. So keep your thumb on that one. Let's go back to the simplification supposition with me. While I think what your natural inclination was to suggest that it's not in simplest form was that you saw that our A value and our C value could both be reduced by 2. Our B value is 1. 1 cannot be reduced by 2. So this is in fact in simplest form. As you suggested, however, we do need to do one more thing to get this into standard form. What is that? How do we do that? Yep.
Can you swap x, just switch it places with y? So you'd have 1y plus x, negative x, 8x to get that. Could you do that?
Well, while this certainly isn't leading with a negative number, which meets our first restriction, if you recall, our x term has to come first, followed by our y term, followed by our c.
So you could add 8 to both sides, and you get 0x plus 8y.
Well, adding 8 to negative 8x gives you 8 minus 8x, because this 8 is being multiplied by an unknown variable. You can't add a term to it to cancel it out. What you would have to do is divide or multiply a term to it to get rid of it. And I think the step is a lot more simple than all of you are trying to make it. What I would suggest is simply multiply this all by negative 1. Whenever you multiply this equation by negative 1, you're left with 8x, because the negative times the negative is positive, minus y equals negative 10. Is this in standard form?
Yes.
If we check it with all of our restrictions, we're no longer leading with a negative number. We've already stated that it is in simplest form. Both a and b don't equal 0, and there are no fractions, so I would certainly agree that this equation is now in standard form. With that being said, can anyone tell me the a, b, and c values? Yes?
A would be 8, B would be 1, and then C would be negative 10.
Negative 1. That is correct. You cannot forget about this minus sign. One thing that may be tripping you up about that is that our equation has an equal sign here. Because of that, if our equation has a minus sign, we have to express this as plus or negative. Does that make sense why we would do that? Yes, are you sure? Because you were looking all over the place whenever I asked that question. Yep. Alright, how much time we have left?
5 minutes,
5 minutes, 8 minutes?
4 minutes.
4 minutes. Alright, so I would say we don't have enough time to go over the book examples. However, one thing that I need from some of you, certainly not all of you, but at least 2 of you, I could certainly use some help. After this class, I need to interview some of you, just to get an idea about how the lesson went. So just to get a quick judge of the class, who kind of thought the lesson went well? Yeah, a few of you. Is that to say that the rest of you thought it went poorly? No. Or that it just went okay? Alright, I'll need one person who thought it went well and one person who thought it went poorly.
Well, there were some things that was unclear to me, but other than that, I thought it went really good.
Okay.
So does that still count as really as well?
Sure, yeah. If you would like to help me out, that'd be great. I need one other person who I can interview. I'll just ask a couple of questions. You will be maybe 5 minutes late to your next class, but it'll be excused. So if anyone can help me out, please just see me after class.